Students, here I am. We are going to discuss about the digital electronics. We are going to discuss how the system will work. As I promised, I will upload one video on the digital electronics, how the system will behave. Okay, how the system will work in a certain manner. Okay, and one more thing I just discussed, as I promised, that I will go side by side for certain things which are very much required for digital electronics. We have to understand that how the digital electronics will come into the system, why we have to study. Most of the students asked me this question, so that's why we have to study this digital electronics. My simple answer to them that when we talk about digital electronics, what you understand from digital electronics, that is very, very important, right? So digital electronics is one which is going to deal with numbers. Digital electronics is one which is going to, work in an integrated environment. So we will study today in a session about how we can implement it, why, what are the different implementation strategies we can follow. So let's talk about digital electronics now. There's a digital signal representation in front of you, and I hope you're able to say it very clearly. So what digital electronics is basically that 0 and 1, the data is with the form of 0 and 1, and we are getting a digital signal, but this is discrete time signal. So when I say discrete time signal, that means the frequency is not concerned. When I say frequency not concerned, like I'm speaking right now, so this is your discrete time frequency signal. But on the other hand, when I say discrete time signal, this is your digital signal. I hope I make you very clear the difference between discrete time frequency signal and discrete time signal. I hope I make you very clear. Right? Because when I say discrete time frequency signal or discrete time signal, don't confuse yourself so much. Just make it understand that yes, when we talk about discrete time signal or discrete time frequency signal, the only difference between both of them is that how you are going to implement the system. I hope I make it clear. So now in the session, we will study about how we are going to implement it, why digital electronics is required, what are the implementation strategy, and how it's going to work. So if I talk about digital electronics itself, you have to understand two things very clearly, that if you are able to understand about digital electronics, then you are able to implement the strategies or the different electronic environment. Like if I talk about fog computing, edge computing, cloud computing, cluster computing, these are nothing but the byproducts of digital electronics. So in front of you, you have a digital signal representation in which we are having a 0 and a 1, right? And this is about the digital signal representation. I hope I make it clear. So if I move to digital electronics, already the manipulation of various quantities, so we deal with 0 and 1. 0 is nothing but a low value and 1 is nothing but a high value and vice versa. So 4 bits when they are combined together, it's nothing but one nibble and IEEE. And when I combine 8 bits together, I comprise it one byte. Okay, so it can be segregated as 0 and 1. Similarly, when I talk about need of digital electronics, it's about easy to design, it's reliable, it's flexible, it's cheaper, right? So various advantages we have. Similarly, when I talk about analog versus digital signal representation, I have to know two, three things that easy in a red waveform. You can see the 0 is kept at low value and 5 is kept at high value. So that means 0 is nothing but low logic and 1 is nothing, 5 is nothing but the high logic. And similarly, when I talk about analog signal, it's nothing but sinusoidal waveform. So you can see in analog I'm taking a value at every sample, but in the case of digital I'm taking a sample. Okay, at every point I'm taking a value in the analog signal. When the digital I'm taking a value at every point, yes, but I'm taking a sample. Now this sample is very much required, for clarity. If your sample is not very much clear, then you have a problem. Like as you can see, I'm talking about ADC and DAC. You're entering some information to your keyboard, and this is an analog to digital converter. At the output, you're getting digital to analog converter because you require some output in the form of printer, right? And the processing is carried on digital system. I hope I made it clear. So now difference between analog and digital electronics, you are very much aware about it, analog and digital electronics. So I already gave so many examples. You can see analog is a continuous signal where digital are discrete time signals. I am again emphasizing on discrete time signals. Analog is basically continuous waves and digital are basically square waves, and we have a technology in which they are very flexible, less power usage is being used. In front of you, you can see we are having a different application of digital electronics in which you can see Arduino, QR code, they are rapidly moving devices due to high speed and accuracy, greater flexibility. So this is all about digital electronics. So I hope I'm making very clear that why you are reading digital electronics, why it is required, and how you can implement, where it is going to implement. I hope it's clear. Okay. So students, we are here to discuss about number system now, right? So when I talk about number system, you have to understand two things very clearly, very clearly. One, how many different type of number system I am having, how many different types of codes I have, what are the conversions, what are the different decimals value, how the binary, hexa, octal will work out, right? So as you can see, beta, as you can see, students, I am in the profession in the last 22 years, right? And I'm making this video on a very simple software, right? And as I promised, beta, without logic you cannot move in engineering. So I always try to inculcate the information as much as I can, right, with best of my ability. So coming back to it, see, when I see number system, you have to very much clear what kind of number system is associated with what kind of terminology or technology. I'm using the word terminology and technology, both are different. Like in the case of number system, you can say 16 is there, 8 is there, or 10 is there. So when I say 10, it's decimal. When I say it's 8, it's octal. When I say 16, it's hexa. Simple as such. The different number of type of number system you have. So this is very, very important. Right? I hope I make it clear. So weighted number system, you can see decimal we are having 0 to 9, in binary we have 0 to 1, octal we are having 0 to 7, hexadecimal we are having from 0 to 9, because after that we are going to have a decimal, then A B C D E F, base 5, 0 to 4, and 8, 4 to 1, and other value BCD code, binary coded decimal, जिसमें आप समझ सकते हैं, राइट? तो हमें जरूरत नहीं है बाइनरी कोडेड डेसिमल के अंदर कि हम उसको सॉल्व करें डिवीजन में. यू विल सी what I want to convey. Now see over here, decimal to other base system, you can see we are dividing from top to bottom, right? So you can see I am having 3345.10. I have to divide it. Simple as such. Don't confuse with LSB and MSB. Otherwise, they have a significance. LSB is least significant bit, and MSB is most significant bit. But however, if you're not that much clear, no problem. Keep it simple, bottom to top or top to bottom in front of you. See, I want to convert decimal to binary, so I'm dividing by 2, 14, 7, 3, 29, 24, 28, remainder is 1. Divide by 7, 2 into 7, 14, remainder is 0. 2 into 3, 6, remainder is 1. 2, 1, 2, remainder is 1, and we can write it. Similarly, we can given a fraction. If you are having a 0.15, multiply by 2, you will get 0.30. Then 0.30 into 2, 0.60, 60 into 2, 1.20, and take 1 out, 0.20 into 2, and so on. So you have to write from top to bottom or bottom to top. That you have to remember. Otherwise, you can keep LSB and MSB also. So decimal to octal. Again, in the same way, you have to divide by that particular radix number, that is 8. Okay, so 8 9 72, reminder is 1, so you can write particular thing in octal way. Similarly, 0.4375, you have to multiply by 8, 3.5, take 3 out, 0.5 into 8, take 4 and 4, you can write out. So this is where you can write decimal to octal, decimal to hexa. Same thing, the decimal to hexa. I hope I make it very clear, divide by that particular radix number. So summary of these numbers, when I talk about, you have to understand in decimal number, we are talking about 0 to 9 used by humans, as I have told you. And other decimal numbers are being used by computer itself, and the language of computer is nothing but hexadecimal. Right? This is binary to hexadecimal. You can see we are having a pair of numbers. In hexadecimal, we are keeping a pair of 4 bits. In octa, we will keep a pair of 3 bits, and so on. Right. So we have to remember that, see, the decimal was the decimal of the default system. For that default system, you can convert to any particular number system. But when I need to convert from one base system to another base system, then I have to think. Right. So this is the way that you have to convert into the one-pair interaction. This is hexadecimal to binary. You can keep this 240A.3C. I divide it into 0010, 0100, I write in their values. This is A is nothing but 10 in hexadecimal. That you have to remember, right? In 8, in octal this A value is not 10. Okay, in octal, this A value is nothing but, because it is 0 to 7, and then it will start. Okay, A, B, C, D. So A is 8 over there. It is in hexa, it is 10, so we have to consider over there. This is binary octal and vice versa. So you can keep a pair of 3. You can have a pair of 3 because of the octal. In octal, the maximum value weighted value is 3. In hexa, the weighted value is 4. I hope I make it very clear. Please tell me. Please tell me. Write in a comment if you like it, you don't like it, or any kind of comment, any kind of query. I would definitely give you the answer with best of my ability. Please. So you can see on 0, 0, 0, it's all 0. In comparison number, you can check out now in octal, you can see that after 7 there I'm going to start with 10. Okay, so in decimal it is 8, but over here it is 10. Similarly, over here it is 9, it is 11. Okay, and this is how the number system works. This is the conversion in front of, don't use calculator. The value is 33 in decimal. So see, now the question arises, so can we solve it using BCD? One of the student asked me. See, the answer is you cannot, because we didn't ask you about the conversion using the weighted function. I hope I make it clear. Because if you want to write 3, 3, that is 0, 1, 1, 1 and 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. That is not exactly the same. And you won't get the same value because they didn't ask you for weighted function, that is binary coded decimal. I hope I make it clear. Is it okay? Yes. So students, now we studied the previous sessions about their number system, what is binary, what are the different kind of advantages of digital electronics and all. Now we are into the concept of binary arithmetic. Remember one thing: it is totally different from your logic. It is different from your Boolean. It is arithmetic. So if you remember, see, might have studied in your 3 different gates. We have 3 different types of classification of the gate. One is basic gates, second is universal gate, and third one is other gates. So in basic gates, we are having and or not, the 3 basic operation. In universal gate, we are having a NAND and not. In other gate, we are having an XOR and XNOR. But in binary arithmetic, we are going with addition, subtraction, multiplication, and division. So just see to it. Is the one thing that I keep in front of you. 1 plus 1 is 0 will carry 1, which is not acceptable and definitely in good tables of the logic gates. Binary addition, Keep it very clear. When the two values are having a value, they are identical in nature and having a high value, the carry would be 1 and sum would be 0. The carry would be 1, the sum would be 0. I hope I make it clear. That whenever the two input values are there and these two values having a high value, then the carry would be 1 and sum would be 0. The carry would be 1 and sum would be 0. Whenever the input having a value, whenever the input is having a value, okay, and identical value and high value, then your carry would be 1 and sum would be 0. Similarly, you can subtract it. Okay, so 1 plus 1 is 0. I'm taking one example. 1 plus 1 is 0. 0 plus 1 plus 1 is 0 with carry 1. 1 plus 0 is 1. 1 plus 0 is 1. Then 1 plus 1 is 0 with carry 1. 1 plus 1 is 0. 1 plus 1 is 0 but carry 1 was there, so we added it. I hope I make it clear. Now you can see the answer is the 7 bits, but the inputs are the 6 bits. Okay, so over here we talk about sign convention, and I will discuss in later on the sections and how the sign convention will look on. Now this is your binary subtraction, in which you can see when we are talking about when we are subtracting a lower to higher value, 0 minus 1. Otherwise, every operation is same. 0 minus 0 is 0. 0 minus 1 is 1 with borrow 1. 1 minus 0 is exactly same 1, and 1 minus 1 is exactly 0. So it's not a problem. But when we are talking about lower to higher, we have to think about it. And over here, I just want to emphasize second complement and first complement. The second complement of negative number is different, but second complement positive number is going to remain same. That's the one trick we normally use. Now, in the binary multiplication, as you can see, we are having a two inputs, and see, whenever we have to study something, we have to just understand the significance of it. Now, 0 into 0 is 0, 0 into 1 is 0, 1 into 0 is 0, and 1 into 1 is 1. So that means if the inputs are high, both are high, then only the output would be seen, and this is nothing but your AND gate. Similarly, binary division. Binary division, in which we talk about 110, we divide it, we get it done. And let us take one example. Like I am having a 000 this is nothing but 6. And this is 101010, this is nothing but I think 42. And I have to take care of this now. So I am multiplying by 1, all are 0. So I am writing 110. Now see, 0 minus 0 is 0. 1 minus 1 is 0. But when I talk about 0 minus 1, it's 1 definitely. But with borrow 1, and that would be more. So what I'm left with now, 0, 0, and next is 1. Right? Now again multiply by 1, 1, 1, 0. 1 minus 0 is 1. 0 minus 1 is 1, no doubt, but the borrow is cancelled and that will be 0. So what we're left with? 1, 1, 0, and then we can multiply by 1. So that's how the binary division would be considered. I hope I make it very clear. You understood? This is one of the example. Do it with yourself, try it, and get it done. So this is all we discussed. Now we are going one step ahead. Now we are going to talk about signed number representation. अब तक whatever we studied, अब तक हमने जो भी किया है पढ़ा है, whatever we studied about about we studied about the addition, subtraction, binary number system, digital electronics, its application, its advantages. But today we are going to discuss. Now we are going to discuss the sign number representation, which is very important and different from your first and second complement classification number system. So binary number system is basically unsigned and signed. Don't get it confused. Keep it simple, signed and unsigned number. So signed is basically signed magnitude and complement, which is, can be first complement, second complement, and we are having an unsigned number also. Similarly, when we are having a zero value, then it is a positive number, otherwise negative number. Let it understand by the example. We are having a minus 10 and plus 10. Now write your 10 value, that is nothing but 1010. Okay, that is nothing but 1010. I think it is okay. Sign magnitude format, that is minus 1, minus 10 plus 10 is 1010. So when I say 1010, I want to see in a positive value that would be 01010, and in negative I am adding 1. Simple. I hope it is clear. So for additional bit that we have to see, that is positive, whether it's negative. Similarly, in first complement, I already discussed the first complement of A is minus A, where the first complement minus A is plus A. So its first complement is nothing but the inversion process 0 to 1 or 1 to 0. And we have to take the second complement value whenever the negative number is there. I hope it's clear. Plus 12 and minus 12 again. 12 you know very well. How can we write it? We can write it 1100. Now one of the question asked by one student of mine many years back. He just asked me, sir, can we say plus 12, can we say minus 3? And same question asked today also. So, this is a general question. But you have to remember that when we're talking about 0 to 15, when you're moving more than 8, less than 15, you're talking about 4 bits. And when you're talking about 4 bits, that means you're talking about negative number. If the fifth bit is added, or the value 1, if the fifth bit is added or number 0, value 0, it is a positive number. So keep it simple. अगर आपके पास बिट्स वैल्यू कंप्लीट हो रही है और एडिशनल बिट मिल रही है तभी आप उसको पॉजिटिव नेगेटिव के कंडीशनल सिचुएशन में लाएंगे अदरवाइज नहीं. I hope I make it clear. Second complement format again. So second complement negative number is a negative number. So we take second a is minus a and second complement minus a is plus a. Right? So represent plus 3 and minus 33 same. Write a plus 33 and then add plus 33 minus 33. In minus 33 second complement, you have to take the first complement and then add 1 to its last bit. So that will give you the second complement. So various steps are been taken. Once complement the negative number, perform the addition, and then if the MSB is 1, then it is negative number. If the MSB is 0, then the positive number. So that is how one example we can take it. Now write 23. You know very well how you can write 23. Don't use BCD over here, please. I again keep on repeating. Don't use BCD. BCD is only come into the system whenever it is asked to be. Otherwise, no. So binary of 23, 10 26. Just write it. Okay, just simple write it. Take a first complement of 23 because it's minus in nature. Okay, so number of bits need to be matched up with the 36. Okay, so we can add extreme to the extreme left, we can add 0, add 1, and take a second complement, and then you will get plus 13, which is the required answer. So this is for the first and second complement. Okay. Now let's talk about now types of binary codes in this session. What the binary codes is all about. When I talk about binary codes, we have to understand from two perspectives. What is from the security purpose and from the evaluation purpose. So we are having a weighted code which can be BCD and non-weighted code which can be access3 and non-weighted code. So you can see the weighted codes is nothing but 8421 by which we can see the positional weights. We can see that at every bit the value is there. Okay, so this is your weighted codes. Non-weighted codes like 0 plus 3, as you can see this number is 0011. So you can easily add it and you can easily get a positional weight for this. This is weighted A4 bit BCD code. Again, I am repeating. Now, this is a BCD code, so you can divide this 278 in a segregated manner. But that is not till the point the decimal number is not attached to it. Right? So now let's talk about very important code that is normally used for the security purpose. And over here, I just want to just emphasize that when I talk about access3 code, binary to access is possible, access to binary is not possible, right? And so for gray code or binary to gray to binary, both are possible, right? So you can see the binary is here and the gray is here. So just remember we are going to do the XOR operation. Keep one bit as such 1. Now 1 plus 1 is 0. As you know that in the XOR operation, if the two inputs are same and identical, the output would be 0. So 1 plus 1 is 0, 1 plus 0 is 1, and 0 plus 1 is 1. Same simple as such. I hope I make it clear. If any query, you can write in a comment. You can like it or not like it. Write it as such. You like it or like it in the way I just communicate to you. Okay. Coming to the binary to gray now. Gray to binary now. Take a one bit as such. 1 plus 0 is 1. Again XOR operation, but in a cross addition. 1 plus 0 is 1. 1 plus 1 is 0, and 0 plus 1 is 1. So this is how the binary to gray and gray to binary conversion is possible and used for defense purposes and even the security application. Now let's talk about logic gates. I already told you, we started from digital electronics, we started from advantages, we segregate into a number system, then we segregate in different codes. Before the codes, we go with addition, subtraction, different operation. Now we are limiting ourselves to logic gates, okay? Because logic gates and addition, subtraction is totally different. They are not going to club with each other. Now let's talk about basic logic gates. I already discussed that when I talk about logic gates, is nothing but what I can say. It's nothing but the basic logic gates, universal and other logic gates. And when I say these gates, remember the concept that when I say about these logic gates, I know it's and, not, and or, but universal logic gates I told you NAND and not. So basic logic gates only come into the picture when I say that yes, the basic operations can be carried out. Now you can see not logic gate. In not logic gate, you can see when you're giving an input of A, you are getting an output of Y, and inversion is possible. So it's just a buffer. Okay, it's just a buffer with input and output having a relationship opposite to each other. Similarly, when I'm talking about logic gate, the AND logic gate, we know that when the both of the inputs are high. Now, this AND gate we normally use in burglar alarm. Okay, so application. Just try to understand the application. Burglar alarm is you have to close down all the inputs from where the inputs are coming. So if the both inputs are high, then the output would be high. The burglar alarm would operate otherwise. Similarly, OR gate, any of the input is high, the output is high. We can use in two-way switch, we can use in staircase wiring, we can use in two-way switch, we can use in staircase wiring, we can use in multiple operations, right? And this is possible that if we are, see, we have to see the application, na? We have to see the application. We should not be very much limited to our. Yeah. So before this, we have to understand the number of logic gates, right? Because most of the students, most of the students they didn't remember the number of the logic gates. So please understand this that the number of logic gates are very important whenever you are going to operate with Tinkercad, whenever you are going to operate with certain mechanism. Okay, so like in NOT logic gate, you can see 7404. Okay, if we are going with the AND gate, the logic is totally 7408, the input logic is 7408, or the gate number is 7408. Similarly, all logic gates 7432 and vice versa. For NAND it's 7400. So understand this. In NAND logic gate, you can see when the output would be every time high if any of the input is low. Right? So we use NAND gates in some full adder, some full subtractor. So you have to think. You have to think where the logic gates can be used. You have to develop your thinking. Okay, that is what about engineering is. NOR gate. Again, in this we will come into the system when the inputs are both inputs has to be identical and having a low value. Okay. Similarly, XOR, when the inputs are not identical, you are getting an output. So these are some basic gates, some universal gate that you can form, and some AND operation or derivation of the OR gate can be done. Various theorems can be comprised to it. So that is totally practice. Go ahead to it and just see how the logics can be made. Again, from the using XOR gate. So what we started now, we studied about the Boolean algebra. Now, we studied about only the truth table, which is nothing but a relationship between output and input, But now we are talking about Boolean algebra, in which we talk about different properties. Like, have an example, 0 plus a is nothing but a. Can I add any value? 0 plus 1 is 1, 0 plus 0 is 0. 0 into a is 0, simple. 1 plus a is a property of 1. Okay. A plus B is commutative and associative law. The most important law that we normally use in B and C of distributive law. Don't cram it. A is the primary function and B and C are a secondary function. So when you are going to write A plus BC, it can be A plus B into A plus C. It is nothing but sum of product and product of sum. Similarly, the third one, a plus a bar b, where a is the primary function and a bar b is the secondary function. So if I am using a bar plus ab, I will get a bar. The answer would be a bar plus b, right? So this second and third function distributive law is very important. Similarly, this in the inheritance law, that is identity law. So a plus a is a into a is a plus ab, you can take a common, 1 plus b, 1 plus b is nothing but 1, so a into 1 is a. Similarly, a into a plus b is nothing but a, right? So you have to understand these things, how can we apply? Simple law, complementary law, a plus a bar is 1, a into a bar is 0, a bar of bar is a. And similarly, we can apply De Morgan theorem, which is very important when we talk about the duality. Because De Morgan theorem is going to work, is going to operate with duality. Right? So x into y plus z bar, where we talk about x bar plus y bar into z, where we can replace 0 and 1. Similarly, this is a into b plus c. These are nothing but, the De Morgan theorem can be applied to 3 or 4 variable. It is not only limited to 2 variable, and we can write SOP to PUS or PUS to SOP. One example, let's take. This is AB plus A, B plus C plus B into B plus C. Just open it. It is like this. AB plus AB, that is nothing but A plus A, that is A. Then AC, B plus BC, take 1 plus C common, what you will get? B. So this is the final answer that we get it. Similarly, you can solve it. This is a practice. Certain Boolean algebra, we can practice it with the different laws of Boolean algebra. Yes. So anyone can write a comment if some kind of query you have. Yes. So let's talk about now classification of Boolean expression. Now, what this Boolean expression is, we are talking about SOP and POS. It is a one-way ahead step to your K-map. Where we talk about SOP and POS, it's a sum of product and product of sum. And when I talk about sum of product, it is nothing but we're taking a product and it is being summation to each other. And similarly, POS. If over here, I just want to keep you mention the POS and SOP are basically replica to each other and inverted to each other both, right? Let's separate. So as I told you that we are talking about min term and max term. So in SOP we are talking about min term and POS we are talking about max term. And in min term we are keeping one high, zero low. In POS we are taking zero high, one low, and vice versa. So this is your SOP and this is your POS, right? This certain values are there. So as I already told you, the POS bar is nothing but SOP. POS bar is nothing but SOP. These are some min term and max term. Min is basically represented by small m. Max is represented as capital M. So different values can be written. Let me give me one example. Now this is 0. So how you will write A bar, B bar, C bar, but automatically in max term it would be A plus B plus C. All are inverted. Take any example, say 6. This is 110. So it would be written as min term because I'm taking one high, 0 low. A, B, C bar, but in next term it will be written as A bar plus B bar plus C. I hope I make it clear. You can see the product in between, a product is there and sum is in between. Similarly, the product of sum is there and we are keeping product in between. So, but if you see clearly in some of the three variables, we are having two variables and these are not very much confined to it. So we move to canonical form. Now, what this canonical form is all about? what this canonical form is all about. When I say canonical form, this means that I am going to have every variable in a pattern or the regular pattern is formed or the regular pattern is formed. This is what canonical form is all about. Right, so let me take one example from you in a canonical form. Now let's see. This is AB plus BC plus AC. Now one is left, that is C, so I'm taking C plus C bar. BC, A plus A bar, and AC is nothing but B plus B bar. Just open it out and just see the omit the repeated product terms, and you will see that yes, certain kind of values you will see. See, it can be AB plus BC plus AC, right, and it's going to be clubbed together. So that is how we can see the canonical form altogether. This is very important concept of canonical form in which we need to understand that how these values are important to us. So we have to expand it. So we have to expand it to a certain value so that every variable should have a significant contribution for the same. POS is standard POS form in which we have to add it. So if you have to have it, we are adding A into A bar, B into B bar, or C into C bar, and that is a zero value. Similarly, you can say M0, M1 that I am discussing with you in detail. So this is about midterm maximum. If you want to write a particular value, you can see it will be definitely clear out because sigma m is representing the SOP and pi m is representing POS. But in this way, you can write it. So now we are on the last leg of our session in which we are going to discuss K-map. I hope you understood each and every topic, whatever covered till this time, till this point. We discussed SOP, we discussed the significance of POS, we discussed binary addition, subtraction, multiplication, the gates, digital electronics advantages, Boolean algebra. Now we are on the last lab, that is K-map, and that is wonderful technique, I must say, for the simplification of complex expression. Now, before I move further, I have to talk two, three things very clearly. When I say 2 raised to power n, don't cram it. I again repeat, don't cram it. Say you are having a two variables. Now this is 2 raised to power n, 2 raised to power 2, that is 4. So total blocks how many? 4. And what is the maximum value you can have? 0, 1, 2, 3. That's it. So let's go to K-map. We have two variables, A bar and A, and see the pattern need to be followed. This is one very important feature of K-map. Say if you are having a 0, 1, so it would be 0, 1. If you are having a 1, 0, it would be 1, 0. Similarly, three variables, you can B bar, C bar, B bar, C, B bar, BC or BC bar. It would be same as POS also. It will be same as POS also, but it can be for four variables or two variables as such. Certain steps are being followed. First of all, you have to understand whether it's SOP or POS. For SOP, we are keeping value 1 high. For POS, we are keeping consideration 0. Okay. So some rules are there. Adjust cells as in front of you. You can see the adjust cells. The outermost cells can be paired. Corner cells can be paired. Extreme outermost columns can be done. Right. This is a wrong thing. I keep it in front of you. The only thumb rule for the K-map, we go with first of all oct, then quad, and then doublet. So wherever the doublet is there, we have to go with the quad. Where the quad is available, not available, we have to go with the oct. If oct is not available, then we can go with the quad and doublet. I hope I make it clear. One again thumb rule that if any element is not considered, if the overlapping of the groups is there, then we can make that element also consideration into the picture. See what I'm talking about. The groups may be overlapped, but the additional elements need to be connected and the diagonal elements not to be present. The diagonal elements not to be present. So you can see we are going with the different oct, then we are going with doublet, and then we are going with pair. That's one example that will be more clear. Now let's have 1, 3, 4, 5, 7. I put all the values. You can see I'm going with one pair, one group, and two groups are there. So the answer would be in the two groups. On the other hand, if I'm having a three group, the answer would be in a three groups. You can see over here I'm going with one quad. These are again one quad and other is another quad. So the elements can be overlapped, but the condition that any other element has to be added. Otherwise, we cannot repeat the same group. This is POS, where precedence 0, 0, right? And the other values we can consider. We now in this we are having two groups. But now the question arises, sir, if one element is left, what can we do? The answer is if one element is left, we are given don't care conditions, which is represented by summation of d. Like in this case, you can see this would be left out. Okay, we cannot repeat it again, and or we can repeat it again, but in the doublet form format. So we go with the quad, and this is about the don't care condition, which is very important feature of K map. I hope I made it clear. I hope I make it clear. So we can gates, and this is about the don't care condition, and with the multiple don't care conditions are there, and we can club them, and you can see the two groups are there. We club them and get a solution. So this is all from this session. I hope you understood. Any query you have, you can reply in a comment. You can contact me on my Twitter handle, on my Facebook account, on my Insta. I'm on my LinkedIn. I'm available. So my only objective to keep this session active, that any query about the digital electronics or if some ambiguity in the mind of the student that this cannot be done, it should be removed and everybody understand the basic concepts, because otherwise, see, you cannot cram so many things in engineering. It's very humble request from my side. I hope you like the session. If you like it, you can comment over there and you can subscribe also. Thank you.